In this video, we are going to get into the topic of annuities. Okay, so an annuity is a stream of constant payments, but unlike a perpetuity, an annuity does end. Okay, so it's basically a set of fixed payments, right? So if you start off with a value and you go, and this has a definite end date, all right? So you'd be getting cash flows, but this would be the end, and then it stops. So annuities are basically one of the more common cash flow patterns that we're going to encounter, right? Because this is basically how most of our consumer loans here in the United States work, right? You borrow a bunch of money on a car, and then you pay it off over time with fixed payments, but eventually you stop making payments because you've paid back the loan. Mortgages work like this. Student loan repayment works like this. So tons of things have this cash flow pattern, right? So what we want to do is develop a formula so that we can find out what the equivalent present value of these future cash flows is. Now, again, as always, we could generically write down this present value as equal to the present value of these future cash flows, right? And so we could take each one of these, right, on and on and on until, we have added up, right, and I'm going to put that T there to show this is the last cash flow, right? So the big distinction between an annuity and a perpetuity is a perpetuity goes on forever. An annuity does have a fixed maturity date or end date to this cash flow stream. So this is the net present value, but we want to think about, is there a better way or a shortcut to doing the NPV that actually makes it less tedious? Because the thing is, if you're looking at the annuity on your home loan, on your mortgage, if you're making monthly payments for 30 years, this T becomes 360, right? Your final payment is 30 years from now or 360 months from now, and that is a lot of cash flows to do all this math with. So is there an easier way? And the answer is yes. Okay, so the proof that we are about to do to show where does the formula for an annuity come from. All right, well, what I want you to do is think about this timeline. Okay, so this timeline says that, hey, you've got these cash flows that go out and they stop at time T. And I mentioned that the only difference between an annuity and a perpetuity is that the annuity stops. All right, so let's think about if we were looking at a perpetuity, this stream of cash flows would go on forever, right? You'd just keep having cash flows out to infinity. Well, what if we could find a way to chop off this tail end value from the perpetuity, right? Because we know that a perpetuity present value is equal to C over R. So we know how to value these cash flows if they go on forever. What if we can just chop off this second piece of value? What's left over has to be the value that comes from the annuity. In thinking that through then, if this is the value to infinity, the value that we want to chop off actually is another perpetuity. Right? So if I call this the perpetuity that starts right now, I would also think of, well, what about a perpetuity that starts at time T? Well, the value of a perpetuity at time T is equal to the payment at time T plus 1 divided by R. Okay, now that may seem weird, but if you remember, whenever we calculated the present value, we started with the next cash flow, right? And so this, you can think of it as cash flow 1, but here's the nice thing about a constant perpetuity. this cash flow and this cash flow are the same dollar value because it's the same payment forever. So I really don't need the little notation there because each cash flow in a perpetuity is the same. Now here's what's crazy. Well, this is the same thing. The value of a perpetuity in each time period, it's always the same. And now that may seem crazy, but if you remember back when I mentioned how to think through the valuation of a perpetuity, I said, hey, what if we invest $100 and that then generates a payment of $10 every period because your interest rate is 10%, right? And in that little scenario, the account always ended up with $100 in it at the beginning of each time period. Well, that's kind of what this is saying, is that if you value a perpetuity, no matter when you value it, it has the same value. But now here's the trick. It doesn't have the same value today, it has the same value in the future. Okay, so what we need to then do is say, all right, well, if this is the value of the perpetuity at time t, these cash flows have to then be discounted to a present value, right? So we've basically made this system of two different perpetuities, and I want to find out the difference, but this perpetuity starts in the future, so it's not worth quite as much. All right, let me clear off some board space and we'll work through this with a little more detail. Okay, so I said that, we've got this whole thing which represents, a perpetuity that goes on forever, but then there's this piece, this whole value, which is the perpetuity at time t. And here's the thing, this is at time 0, this is at time t, so I need to discount this back, right, to time 0. And so the way I do that is I will take the present value at time t divided by 1 plus r to the t. And this will calculate the present value at time 0 of this value at time t. All right, and so now what I need to do for the present value of the annuity, it's going to be equal to the present value of the entire perpetuity minus the present value of the annuity that starts out in the future, and that's going to be C divided by R over 1 plus R to the T. All right, now this is not how you will usually see the annuity formula written. What they're going to do is they will pull out the common C over R, right? And so you might see C over R times 1 minus 1 over 1 plus R to the T power. And then they will also sometimes do a second step where they will pull out the C as well. All right, so cleared out a little bit more room here to work. And like I was saying, they often will do like a little second thing here where they will just have the cash flow times 1 over R times 1 minus 1 over 1 plus R to the T power. Okay, and this is often how you'll see it written. And there's a reason that they write it like this a lot of the times, and that's because often we will break this piece out separately from the payment. Because here's the thing, this second piece of the formula is what we often call the present value of a future annuity. It's the present value of interest factor on an annuity. And what that means is if you take the payment times this whole second piece, that is the present value of that annuity of payments. Okay? And so this can be thought of the present value of this annuity if you're getting $1 payments. Well, if you multiply that times the number of dollars that each payment has, then this is a number that we just multiply our cash flow by, and that tells us the present value. So you will often, and less these days, it used to be more common that you would have big tables where someone would have already worked out the math of, given the number of payments and the interest rate, here is this, annuity interest factor. And you could just go look up this number in a table, say, okay, well, here's the dollar value of each payment, multiply it by this number, and this is the current value of that annuity stream. And so there used to be these big tables of this. Now, the next part to see is, well, if you're thinking of, hey, this present value factor, what if I want to calculate the payment? All right, now this is where things get useful, all right? Because again, remember, this is a representation of ANPV for cash flow patterns of annuities. And I mentioned that these are pretty common in consumer loans. So, another way to think about this, if you buy a house, that is worth this much money, and you want to know what your payment is going to be, you divide the value of the house by this interest factor, and that tells you your payment, right? Because this is the interest factor on an annuity at this interest rate for this many time periods. And so basically this would be the periodic rate of interest on your mortgage. This would be the number of payments on your mortgage. So if it's a 30-year loan with monthly payments, you would have the interest rate per month as R, and you would have 360 as T. That's the factor. And if you take the value of your home divided by that factor, that will tell you, here's the payment that you are going to have to pay on your mortgage for the next 30 years. Now, having looked at basic annuities, the next thing that we want to take into account is, just like perpetuities, there are annuities that do not have constant payments. We're going to look at growing annuities. Okay. Now, the only difference, again, is these cash flow payments. Right? So if you have a cash flow in time period 1, cash flow 2 would be cash flow 1 times 1 plus some growth rate, and then this cash flow would grow through time. Basically what's happening is, here your payment is not constant, but again it grows at a fixed growth rate and does have a fixed ending date. Can we do the net present value in a more simple way rather than having to just take a bunch of present values individually and add them all up? Yeah, we can. Now, I'm not going to go through the whole proof again, although it's basically the exact same method that we use for regular annuities, because we do know the formula for a growing perpetuity. You find the value of a perpetuity, a growing perpetuity, that starts right now and goes on forever. You find the present value of another annuity that starts at time t and goes on forever. The difference between those the difference between those two perpetuities is the value of the growing annuity. So I'm just going to jump straight to the present value formula for a growing annuity is equal to, well, here it's going to be cash flow 1, and that is important that you get the right cash flow, because now each cash flow is not the same. But you would multiply that times R minus G, okay? And once again, you would have 1 minus, well, and here's where it gets a little different, because the deal is, whenever you get out here, you actually have to find the cash flow at T plus 1 period, which is going to be a bunch of years of growth. As a matter of fact, it will be T periods of growth. And so you will have 1 plus G over 1 plus R to the T power, all right, as the second term. Now what's going on here is, to get from cash flow 1 to cash flow T plus 1, you have to go T years into the future. Okay, because you're at 1, you're going to T plus 1. Well, the difference is T years. All right, well, if you are growing at rate G for T years, this represents the growth in the payment. Likewise, to get back to a present value, I need to discount by T years, because in the formula, we are discounting from year T because that's where the annuity that starts in the future gets valued. Well, this T is a common exponent, and so that gets captured here. And so this handles getting the future annuity discounted back to today. This piece handles the growth in the cash flow through time until you get to that future annuity. And so this ends up being, you know, the formula for a growing annuity. And likewise, you will often see this as written this way. You'll see this as a big, right, annuity factor. All right, except this would be the present value interest factor on a growing annuity, but otherwise it's used much the same way. Now, growing annuities you don't encounter all that often. You see them a little bit here and there, but not that much. And as a matter of fact, I will say about the formulas in this discussion, in this video, you will rarely, if ever, have to actually use these formulas, okay? Because we are about to get into learning how to actually do this math using a financial calculator, which is going to solve a lot of problems. So you need to see how these things are developed to understand the intuition behind what's going on. But the nice thing is this big ugly formula, I don't know the last time I've ever actually used one. Just not that important. So from this point on, we are about to shift gears and get into actually doing some problems, because this is kind of the last piece that we need to understand about the math before we can really start cranking through some practical applications.